motion of the planet around the sun. So we know that the planets go around sun not in a circular path but elliptical path they are going. But in the advanced level we consider the planets move around the sun in a circular path. So I consider this as my sun. And some this is a some planet, right? It is can be Earth or anything, right? It's going in a circular path. So this is the planet, right? So if some object moves in a circular path, we know that it must have a centripetal force. So in this case, centripetal force supply provided by the gravitational force between the sun and this planet. So I can draw the force as this. This is the force between sun and this planet, and I can write the velocity of this planet in tangent along the tangent in this point. I take it as v. So I take the mass of sun as ms, mass of the planet as mp. Right. I am going to write F equals ma towards the center. Right. So the force acting towards the center is gravitational force. So I can write gravitational force using Newton's law. According to Newton's law, I am going to write it as G ms mp divided by distance between sun and this planet is r, then r squared equals m. I can write acceleration as centripetal acceleration. So the centripetal acceleration I can write as v squared over r. I can cut r to r, and this is also going to be mp, right? So we write f equals ma to the this planet mp. So mp is also going to cancel out. Then I get the value for the g ms divided by r equals v square. Then I'm going to consider the velocity. So we know that the v velocity, I'm going to consider the velocity is a constant, right? Velocity is a constant, uh, and the periodic time. Periodic time means time taken this planet to complete one circle. In this circle, so I can write velocity. We know that velocity equals distance divided by time, right? In the periodic time, when we consider a periodic time, so periodic time it goes one circle. So the distance that planet move, I can take uh, it travel 2 pi r distance, right? So for a one circle it travel 2 pi r distance. So I can write velocity as 2 pi r divided by t, because I consider the periodic time. So I can substitute v squared using this and take some relationship. As you can see, I'm going to substitute g ms r. We know that v equals to 2 pi r divided by t. Then the v squared is 4 pi r squared t squared. Right? Then I am going to subject t squared. T squared equals to 4 5 this also squared 4 5 squared divided by gms into r cube. So by this relationship I can say that the periodic time of any planet, square of periodic time of any planet, proportional to the radius, distance between sun and that planet, cube of distance between planet and the sun. So the periodic square of periodic time of the planet proportional to the cube of distance between sun and that planet. This is the relationship I am obtaining for the considering the motion of a planet around the sun. So this is, you can take this as a subtopic, motion of a planet around the sun. Then we are going to find the equation for the mass of the planet. So next I'm going to mass of the planet. To build the equation, I am considering some planet which is mass is capital M and the radius of the planet from the center to the surface is capital R. Right? To build equation, I am considering object released from near the surface. Right? It is very near the surface, so that I can take acceleration as g. This object is released very near to the surface, so I'm going to write f equals ma to this freely falling object. As you know, I can write the force between this object and the planet as gravitational force using Newton's law. So g m, think mass of this object is simple m. Distance between this object, so I consider this object is very near to the surface, so the distance between simple m and the planet m I can write as r square. Right? M means mass of object m, acceleration, gravitational acceleration. As you can see, I'm going to cut out. Then I can get the, I'm going to subject mass. Then mass is g r squared divided by g. So you can use this equation to find the mass of any planet. So you have to substitute. So when you're using this equation to find mass of a planet, you have to substitute gravitational acceleration on that planet. This is, you cannot use g as 10 for the all planets, right? G is 10 only on the earth. When you use this equation for other planet, you have to find the gravitational acceleration on surface of that planet, right? It is not going to be 10 always, and the r is the radius of that planet. It is also vary with which planet you are going to use this equation, right? So I am going to define g is the gravitational acceleration on surface of that planet of considering and r is radius of planet, right? G is a constant, it is a universal constant, so it is not going to change anywhere anytime, right? So it is a constant, so G and R squared vary, then you can find the mass of any planet, right? So this is the equation, and by this relationship we take very famous substitution, which Gm equals Gr. This is very famous substitution, you have to remember it. It is going to use for a MCQ, right? So we can use this equation for any number of planet if we know the mass, gravitational acceleration, and radius of those planets, right? This is a very famous one, you have to remember it also, right? So we found the mass of the planet, and we can find the density of the planet also. We know that when I'm considering density of the planet, so we know that I'm going to take density as T. Density is mass divided by volume, right? I know the mass of the planet, it is Gr squared divided by G. Volume is volume of the sphere, right? Volume of the sphere is 4 divided by 3 phi r cube. So by simplifying this, I can take equation for the density of any planet. It is 3g divided by 4 phi r capital G. So you can use this equation for any planet, but the above conditions apply to this also. So the G be the gravitational acceleration on that planet, r is the radius of that planet. So then you can find the density of that planet, right? So if you know this equation, it is very easy to solve MCQ problems, right? In the essay papers, maybe you have to prove this equation. Proof of these equations are very simple, as you can see. In next video, we are going to talk about satellites and geostationary satellites. See you in next video.